Hi, I'm Benny Cutler. I'm from NSU University School, and I'm here to help you study for your AP Calc exam, which is coming up very, very soon. So today I'll be covering Unit 7, which is differential equations. It's probably one of the easier units because it's not really a new concept. It's just using derivatives and integrals to solve certain problems. So let's jump right into it. Okay, so the first thing they want you to understand is proportionality in differential equations. So basically what a differential equation is, it's like any other equation, like this is proportional to this, except instead of like something like people, it'll be a rate like people per year. So let's look at this one. It'll be better to see it in an example. So a pharmaceutical company is trying to find a new treatment for a certain disease. They're adding material M to a petri dish full of diseased cells. Once the material has been added, readings are taken at intervals to determine the number of diseased cells C that are present compared to the weight of the material M. The head of the research team has determined that the rate at which C is decreasing with respect to M, so let's write that out. Rate at which C is decreasing with respect to M. So we can write out the rate at which C is decreasing with respect to M. So this is the rate of change of C with respect to M. So how C, which is the number of diseased cells, is changing with respect to the weight. So it says here that it's decreasing with respect to M. So we're going to put a negative sign to show that that the number of cells is decreasing. So the rate should be negative. It's directly proportional to the natural logarithm of the square of M. So if something's directly proportional, it goes in the numerator, which is just being multiplied. So ln, the natural logarithm of the square of M, so M squared. And because it's proportional, we have to add some proportionality constant K, just to show that it doesn't necessarily need to be ln of M squared. It's proportional by some constant K. So in these answer choices, it doesn't have any that are negative. Instead, it just has the expression itself without the negative, so we can cross this negative off. And then it says this rate where K is a negative constant or a positive constant. So first, let's look what we have. It's K times ln of M squared. So it looks like that matches up with all of them, pretty much. But we know that the rate equals this, not the number of cells itself. So right away we can eliminate B and D. And now if we look and remember that we originally had a negative out up front because we knew it was decreasing. So K has to be a negative constant to indicate that the rate of change is negative. So it's decreasing. So this is knowing what differential equations are in context. And that'll set the base for the rest of the unit. So the next thing we want to do is be able to test solutions to differential equations. So like before we had dc with respect to M, now we have dy dx, which is something we're more familiar with. The rate of change of y with respect to x, which is just the slope of a tangent line on a graph. So we know that at any given point, this right here is the rate of change at any point. So what we can do, we have to look at the answer choices that we have and take the derivative and see, does the derivative of that dy dx actually match up with this? And we'll use this initial condition in a second to make sure that everything works out. So if we test the first one, derivative of square root of something is 1 over 2 times that something, square root of that something, plus 7, times the derivative of the thing inside the square root, which is just 2x. So these 2's will cancel out, and we're left with x over square root of x squared plus 7. And if we look, y, our original y value that we started testing, is the square root of x squared plus 7. So this thing on the bottom, we can just write as y, which equals x over y. But if we look here, this is 2x over y. So we know this has to be wrong. It's close, but not quite. And because this is the same thing with just a negative sign out front, this also needs to be eliminated. Now let's try something very similar. It's just 2 times that. So derivative of square root of something, 1 over 2 times square root, 2x squared plus 14, times derivative of 2x squared plus 14, which is 4x. These cross out, you're left with the 2. So you have 2x over square root of 2x squared plus 14. And if we look now, the 2x squared plus 14 was the y we started with in this case. So we can rewrite that as 2x over y. So that's what we're looking for. But we need to know if it's positive or negative. So we're going to use this initial condition. So now that we know that one of these is right, we can just plug in this initial condition for x and y. So x will be 1 and y will be negative 4. So let's just take the positive one here so we don't have to work with negatives. We have y is negative 4 equals 2 times x is 1 squared is 1. So square root of 2 times 1 plus 14. So if we notice, this is going to be square root of 16, which is 4, not negative 4. So that means when we originally plug this in, we're going to need a negative outside to make that true. So that means that this is the right answer because we do need that negative to make this initial condition true. Okay. And later we'll figure out how to do this from scratch without just testing answer choices. But for now, this is what we're going to do. Okay, the next thing they want you to know is slope fields. So this is basically just plotting the derivative at every point of like a set of like a differential equation. So it's just saying when x is something, it's just every point plugged into whatever that derivative function is. And let's say the derivative is 0, then like it is here at 2, we can draw a little line with a slope of 0 to indicate that the derivative or the slope of a tangent line there is 0. And the same thing with this over here, the slope of that is probably 1, 1/2, 2, somewhere, something positive. And then this gets more positive, so the slope gets more positive. So what I like to do for these is just plug in your answer choices. When you're given the slope field and need to find an equation that represents it, well, first thing you can look at is does it depend on x and y? So if we look here, when we go up and down, everything in a vertical line is the same. Look here, it's a line with that slope, same thing. It doesn't change with respect to y. So that means anything where the derivative has a y in it, we can take out. And the same thing would apply for x. If it was the same thing horizontally and it changed only with changes in y, then we could eliminate answers that had x in them. So now that we have this, we can look at the patterns of the graph for the slope field. So on the left, when it's negative and positive, we notice that it's the same. The slope is the same. It's not flipped or anything. So if we look at our two answer choices, we have the derivative is x squared and is x cubed. And when x is negative, x squared is still positive, which matches up with these lines with a positive slope on both sides. But x cubed when x is negative. So that would be a line going down like this. So we know that it has to be c just because it would be negative if it was d. And you'll also sometimes be asked to draw a slope field. So to do that, you'll be given something like the derivative is this, or you'll have to find that in another step. And then you'll just plug in every integer point here. So we'd start with plugging in, let's say 1, for 1, 0, when x is 1 and y is 0. So if we look here, only thing we have is x, no y. We plug in 1 squared is 1. We draw a little line with the slope of 1. Here it's going to be 2 squared. 2 squared is 4. Draw a line with a slope of 4. And you just repeat that for every point here. It's a little tedious, but they occasionally will ask you that. So you just have to be prepared. And reasoning using slope fields. So when you have a slope field like this, or you draw one yourself, they might ask you something about what the solutions look like. So a slope field basically just shows every possible function with different initial conditions. So if we started with the initial condition, let's say it started here, then it would look something like this, and then something at the bottom too. It would be around here. So you just follow the lines to make these. These didn't just come out of thin air. You look at the slope of the lines, and you know the slope around that point is kind of going to be curved in the direction of those lines. You can imagine it like fluid flow. If you have fluid flowing in the direction of these lines, like water, and you drop some more water into it, then where's the water going to go? It's going to follow that path. So it's the same thing with a function. You just follow the little lines. And if we look at what this question is asking, it's asking like what these curves look like, what the solutions look like. So here, if you remember what a hyperbola is, it's this. And if it were, let's say we didn't have this bottom part and everything were just pointing up like a parabola, it would be a parabola. But here, since we had those two little U's, then they're gonna be hyperbolas, the solutions. And if we notice, that doesn't matter. It doesn't matter where our initial condition is. If we had one here, it would still be a parabola. So the initial conditions, you just follow the lines based on starting from wherever your initial conditions are. Okay. Now the big thing in this unit is separation of variables to solve differential equations. So I like to phrase this by saying separate then integrate, and we'll see what that means in a second. So here we're asked to use an initial condition to find a solution for this differential equation. So dy dx, the derivative of the function, is this 3t squared minus 2t minus 4. So you're probably thinking something about integrals, because integrals and derivatives are inverses. But we can't just integrate this whole thing, because we wouldn't know what variable to integrate it with respect to. Would it be dy or dt? So instead of treating this derivative as a ratio that has to always stay as dy dt, we can think of dy and dt separately as small little nudges to either the input y or the output, or either the input t or the output y. So we can treat these as just really, really small numbers, but they're different from each other. So what we want to do is isolate the variables and get them all on the same side. So if we notice, everything on this right side has a t in it, no y's except for this dy right here. So what we're going to do is move this dt onto this side. And if there were y's on the other side, we'd move them onto this side. So this is the separating part of separate then integrate. So now we'll be left with dy equals 3t squared minus 2t minus 4 all times dt. Now this is starting to look more like an integral. So what we can do here is, like we would in any equation, we do the same operation to both sides. And here we do an integral. So we integrate both sides. The integral of dy, you can think of that as 1 dy. So that's going to be, draw an arrow to make sure it comes from that. That's just going to be antiderivative of 1 is y. So y plus c equals the integral of this, which is t cubed minus t squared minus 4t plus c. And these are different c's, so we can't just cross them out. That doesn't work. So, but what we can do is move both of the c's to one side, because a constant minus a constant is still just a constant. It might not be 0, but it's still a constant. So we can rewrite this as y equals t cubed minus t squared minus 4t, then plus c, because if we subtract this If we move this to the other side, this c, let's call it c2 minus c1, it's just going to be a different constant, but we don't really care what the constant is right now, but we will in a second. So now we can look, once we have this function, we have to plug in our initial condition that they give us. This is a general solution, but we want to find a solution with this initial condition. So remember on our slope fields, that's where we start at a specific point and follow the lines. So here, to find the solution with this initial condition, we just have to plug in these values and see what c equals. So when t is 3, y equals 5, because that's what it means for y of 3 to equal 5. It's like a function. So if we take this function over here, plug in these numbers, we get 5, because y equals 5, equals t cubed, so that's 3 cubed, which is 27, minus t squared, which is 9, minus 4t, which is 12, minus 12, plus c. So now we have 27 minus 21 equals 5. 27 minus 21 is 6. So 5 equals 6 plus c. And then subtract 6 on both sides. You get negative 1 equals c. Then you just plug that c right back into here. So it's going to be whatever this is, but c is negative 1. So if we look, t cubed minus t squared minus 4t, all this stuff with the minus 1 at the end. And that is how you separate and integrate. That's the big part of this unit. The next little section of the unit is also related to this. This is the main idea that you have to get from this unit. So now we'll do another one. General solution for this differential equation. So this, they want you to keep the c. They don't want you to solve for c using the initial conditions. Here, you just leave c and let it be. So first thing we notice is there's a y and a t on this side. So we need to separate our variables. So first instinct should always be the thing on the bottom, move it to the other side by multiplying. So we have dy equals yt squared. I don't know why they put this little multiplication sign here. Yt squared times, actually I'm not sure if it makes a difference, but we'll do it again because why not? Dy, if we divide by y first on both sides, then we have dy over dt times y equals t squared. So that's just dividing y by both sides. Y is in the denominator on the left and it's gone from the right. And then we multiply both sides by dt. So now we have dy over y equals t squared dt. So this here on the left is the same as 1 over y dy, which is a lot easier, which looks a lot more friendly to integrate, equals t squared dt. Now I'll erase this just for room because those are the same thing. And now we just integrate both sides with respect to their variables. So the integral of this, the integral of this, integral of 1 over something is ln of that something. So ln of, we have to keep our absolute value signs because ln can't be, you can't take the ln of a negative number. So this is just notation. Equals 1 over 3 t cubed plus c. Oh, there should be a plus c over here too. But remember, constant minus constant, still constant. So we can ignore the c on the left and just have the c on the right. But it's a different constant, but you don't have to indicate that. So if we know that ln is log base e of something. So e to the power of whatever this equals y. So we can rewrite this as e to the 1 over 3 t cubed plus c equals y. And this is close to what we're looking for, but we have to do a little bit more, we have to use a couple more algebra tricks. So we know that when we're adding things in an exponent, we can separate that into multiplying it with the same base. So this can separate into e to the 1 over 3 t cubed times e to the c equals y. Because if you multiply these, you're just going to add the exponents. So that's the same as that. And if we notice e to the c, we're raising e, a constant, to the power of another constant. So this is just a constant, a different constant c. We're a little, we don't really care which c it is. We use c for a lot of things. But if we rewrite that as c, then we have c times e to the 1/3 t cubed equals y. And that's our answer. Okay, let's try another one. So y prime equals this, given that some initial conditions. Okay, so we notice we're given y prime this time instead of dy dx, but they're really the same thing. You just have to rewrite it. So we have dy dx, because that's what y prime means when it's with x and y, equals 2x cubed over 2y plus 1. Now, if we get both variables on the same side, we move this up here, we get 2y plus 1 dy equals 2x cubed dx. Now we can integrate, which is what we want. And for the left side, we have y squared plus y plus c, and then the right side equals to the 4th. So 1/2 x to the 4th. Yes, that's right. Plus c. The c's, one of the c's stays, doesn't matter which one. And now that we have this general solution, we plug in our initial conditions to find c. So when y equals 0, x equals 2. So we just plug in y equals 0 and x equals 2. So 0 squared plus 0, 0 equals x is 2, 2 to the 4th is 16, over 2 is 8, plus c, c equals -8. Then we just put that right back up there. Then we get y squared plus y. If we move this 1/2 x squared over to the other side, minus 1/2 x squared equals -8. And that matches with this. Okay, we're getting close. Okay, another one. This is basically the whole unit, so figured we need some practice with it. So again, we want to separate our variables, get all the y's on one side, all the x's on one side, this up here, move this up here. Y dy equals 3x plus 2 dx. Integrate both sides. Integral of y is 1/2y squared plus c equals 3/2 x squared plus 2x plus c. We don't care about one of those c's. And now we use an initial condition to find c. So x equals 1, y equals -4. So if we plug -4 in for y, we get -4 squared is 16, over 2 is 8. 8 equals 3/2 times x squared, x is 1. 3/2 plus 2 times 1 is 2, plus c. So that 3/2 plus 2 should equal 7/2. Move that to the other side, 16/2 minus 7/2. You get 9/2 equals c. And we just put that right there. And now we have to isolate y because we can't have y squared. We want to find just y by itself. So we multiply both sides by 2. We have y squared equals 3x squared, because the 2 in the denominator is multiplied by 2, so it goes away, plus 4x plus our c was 9/2. 9/2 times 2 is 9. And now take the square root of both sides. Y equals, and remember we have to add a plus or minus square root of this, 3x squared plus 4x plus 9. And if we look here, I believe that is our answer. Oh, maybe it's just negative. So if we take the square root of both sides, and then knowing that our initial condition is that, so we'll have y equals square root of 3x squared plus 4x plus 9. And then we want to check our initial condition one more time to see if the signs make sense, because we have 3 different choices with different signs, and then this weird thing at the bottom that doesn't look like it's going to be our answer. So we want to plug back in our initial conditions. We know y equals -4. But if y equals -4 and y equals the square root of something, then the square root, the thing under the square root would have to be imaginary, which it is not. So the only way for this right side to be negative, to equal -4, is we put a negative sign right here. So the one with the negative sign will be our answer. Okay, last question. Okay, so now we're going to do something similar to what we did in our first example, which is finding a differential equation based on the information they give us, writing one out for ourselves. So if we look at the rate of change of y with respect to x, which is dy dx by definition, it's the little nudge to y caused by a little nudge in x, dx. These are both really small numbers, but remember we can treat them each as a small number instead of a ratio, which is the derivative. Equals is proportional to y, so equals ky. That's all we know right now. So we have these 2 initial conditions or solutions to the curve, which we're going to be able to use in a second. But first we want to get this in terms of y. So we're going to want k to be with our x because we don't have any other x's, and the y to be with the y. So when we do divide both sides by y, we get 1 over y dy equals, and dx times both sides equals k dx. So that's going to give us, when we integrate that, it's going to give us ln of y plus c, which we're going to be able to ignore because we have one on the other side, equals integral of k with respect to x, which is just kx plus c. You can safely ignore this c because the constants are both constants. And now we can rewrite this as e to the kx equals y. And now what we can do is start plugging in these initial conditions. This could maybe be simplified a little more, e to the k times e to the x, but that's not going to help us right now. First, we want to plug in this one that has 0 in it, because that's going to, as we'll see, help us eliminate this k right now. Oh, wait. Of course, I forgot the plus c. Kx times e to the c. Because we know that we're doing e to the power of kx plus c, and that can separate as e to the kx times e to the c. Because when you multiply exponents with the same base, they just add. Now, k times x, when x is 0 in this initial condition, this k just disappears. It's because 0 times something is 0. So we have e to the c times e to the 0, which is 1. So we can just ignore it because we're multiplying by it, equals y is 3. So we'll write that. Then take the ln. That is not an ln. Ln of both sides. Ln. We get c equals ln of 3. And then we can plug that right back into there, or not there. Right back into there, with a loop-de-loop arrow. And now we're going to use our other condition to solve for k. So now we have e to the ln of 3, which is just 3 because by definition, it's e to the what equals 3. We're raising e to that power, so it's just going to be 3. So there's going to be 3 times e to the kx equals y. So this is what we have as our equation now. Now we want to plug in this -1 and 1 solution. So now we get 3e, x is -1, so e to the negative k I'm going to draw that a little better. E to the negative k equals y is 1, so equals 1. So we have 3 over e to the k, because e to the negative k is 1 over e to the k, equals 1. Now we can move things around and get 3 equals e to the k. Now we take the ln of both sides, we get ln of 3 equals k. So that's what we got for the other one. So now when we go back here, when we plug in ln of 3, we're going to get e to the ln 3 times e to the x. E to the ln 3 is 3. 3 times that 3 that we got for c is going to be 9 e to the x. Or actually, wants us to keep it as x ln of 3, which probably means that I did something wrong with the e to the ln, but let's see if it works. And it does. So if we look here, this ln 3 just stays. We didn't need this step somewhere around here where what was it? It was, I'm not sure, but where we were doing e to the kx and we were plugging in ln of 3 for x, I don't think we could just separate that into e to the x times e to the ln of 3. So we would just have this answer. We did more work than we needed to. So whenever you overdo something or underdo something in a multiple choice, you just have to keep going and see what could I do to get it in terms of this answer choice. So if you notice that the answers have ln in them as exponents, then you have to fit your answer choice or your answer to fit the answer choices. Okay, and that's differential equations, a pretty quick unit compared to some of the other ones we've done. It just draws on some past knowledge and helps apply them to a field which is really useful in physics and economics and other areas. So I hope this was helpful, and I'll hopefully see you in some more videos in the future.